All right, let's jump right into a really interesting question. We always think that as AI gets smarter, it's got to get stronger, right? But what if that's not the whole story? What if the very process we use to make an AI super accurate is also making it dangerously fragile? I mean, to really get what's at stake here, just picture this. A self-driving car is rolling up to a stop sign. But someone slapped a small, weirdly patterned sticker on it. Now, to you and me, it's a stop sign, no question. But to the car's AI, it might suddenly see a speed limit 45 sign. And this isn't some sci-fi movie plot. It's a very real, very studied vulnerability in the AI we use today.
And that right there, that brings us to the absolute core of the problem. So let's dig into this hidden vulnerability that researchers are frankly racing to try and fix.
So, that sticker on the stop sign, it's a perfect case of what the experts call an adversarial example. Basically, it's any input, an image, a sound, whatever, that's been tweaked just slightly, often in ways a human would never even notice. And the goal is simple and kind of scary, to make the AI have a catastrophic failure. This is the key. It's not enough to just measure an AI on how well it does with normal, clean data. We have to measure its robustness, its ability to stand up to these kinds of clever attacks. You can have an AI that's 99% accurate, but if it's not robust, it's basically a house of cards waiting for a slight breeze.
Now, the typical way people try to fix this is with something called adversarial training. You pretty much show the AI a whole bunch of these attacked images and say, hey, don't get fooled by these. And it works, kind of. But here's the catch. When you make an AI more robust this way, it often gets dumber, less accurate on normal, everyday images. It's this super frustrating trade-off.
And this is where the research we're talking about today gets really interesting. What if we've been focused on the wrong part of the problem? Maybe it's not about the AI's education. Maybe it's about its very blueprint, its fundamental architecture.
So, to unpack that idea, we really need to look at the two main schools of thought for how these AI architectures get designed in the first place.
So on one side, you've got your handcrafted architectures. These are dreamed up by human experts, built on intuition and just years and years of trial and error. Think of it like a bridge designed by a seasoned civil engineer. They know what works. Then, on the other side, you've got something called Neural Architecture Search, or NAS for short. This is where you use another AI to search through millions of possible designs to find the absolute most efficient and accurate one. This is like a bridge designed by a supercomputer. It's going to be hyper-efficient, maybe using weird shapes a human would never even think of.
And here's the thing you gotta know. These AI-designed NAS models, they're the champs. They are the state-of-the-art. On all the standard tests, they consistently get the highest accuracy scores. For all practical purposes, they are the smarter AI.
But, and you knew there was a but coming, this is where the story takes a huge, unexpected turn. Because it turns out that being smarter doesn't mean you're stronger.
So let me just ask you straight up. Which one would you bet on to be tougher against an attack? The classic, human-designed model, or the new, hyper-optimized AI-designed one?
Okay, let's actually look at the data. This chart from the paper lays it all out. The vertical axis, that's your standard accuracy. The higher up, the better. The horizontal axis is robustness. The further to the right, the tougher it is. The sweet spot, where you want to be, is that top right corner, super accurate and super tough.
Now first, look at that cluster of dots in the top left. Those are the AI-designed NAS models. And just like we said, their accuracy is incredible, way up there. But look how far to the left they are. They are so brittle. They basically crumble the second they face a real attack.
And now, here's the kicker. Look over at the bottom right. See those? Those are the old school, human-designed models. Yeah, their clean accuracy is a little bit lower, but look how much tougher they are. They're way more robust against the exact same attack. It's a total reversal of what you'd expect.
And this is what the researchers call the high accuracy trap. It turns out that when we tell an AI designer, hey, find the absolute most accurate model possible, we might have been accidentally telling it to build the most fragile one too.
So is the answer to just throw out these powerful AI designers? Well, no, not at all. Actually, the researchers figured out this incredibly clever way to get the best of both worlds.
They put it perfectly in their paper. They basically asked, what if this whole NAS process, which is already great at finding accurate models, could just give us that toughness, that adversarial accuracy, as a free add-on without all that painful adversarial training?
And their solution is so elegant. See, that neural architecture search process doesn't just find one design. It explores this giant library of potential designs. So instead of spending all this effort to find the one single best one, the researchers just randomly picked a few pretty good ones. They trained each one and then basically had them vote on the right answer as a team. It's like asking a whole committee for their opinion instead of relying on one single specialized genius who might have a blind spot.
And what was the result? Get this. Just by using this simple team-based approach, they boosted the model's robustness against a really strong attack by almost 12%. That is a huge improvement, and they got it not by changing the training, but just by being smarter about how they used the designs they already had.
So what does all this mean for the big picture? How does this actually help us build AI that's not just powerful, but also safe? Well, the first major takeaway is that accuracy, all by itself, is a pretty bad way to measure how good an AI is. I mean, if a model is 99% accurate but 100% fragile, is it really useful in the real world? It forces us to ask a much better question. How should we be measuring an AI's true strength? And to answer that, the researchers actually proposed a new metric, the Harmonic Robustness Score, or HRS. Instead of looking at accuracy and robustness as two separate things, it combines them into one single number. It's designed to reward models that are both accurate and tough, and to penalize the ones that are great at one but terrible at the other. And that really brings us to the final and maybe most important point. If we want to build AI that we can actually trust, it's not just about giving it a better education with more data or fancy training tricks. It's about getting the blueprint, the architecture, right from the very beginning. The design itself matters, maybe more than we ever thought. So I'll just leave you with this thought. As AI gets more and more woven into our daily lives, in our cars, our homes, our hospitals, we have to make sure we're not just asking if it's smart. We have to ask if it's wise. Are we actually optimizing for the right things, and are we even asking the right questions to know what strong really means?